Hi, welcome to Chapter 13, Properties of Solutions, Overview Part 1, where we're going to talk about the solution process, saturated solutions and solubility, and what factors affect solubility. So solutions. Solutions are actually mixtures, and they are homogeneous mixtures, where you have two or more pure substances mixed together. In a solution, you have a solute and a solvent. Okay? The solute is what you are dissolving. The solvent is what is doing the dissolving. The ability of a substance to actually form a solution depends on two things. One, the natural tendency towards mixing. And two, the intermolecular forces. So let's talk about the natural tendency towards mixing. If you put two gases in a container and they are separated, you're going to have oxygen on one side, argon on the other. If you remove this barrier, the gases will mix spontaneously. So gases mix spontaneously. Each gas acts as if it's alone and tries to fill the container. Mixing causes more randomness in the position of the molecules, increasing a thermodynamic quantity called entropy. Entropy is really randomness. And randomness wants to increase, okay? The universe wants to move towards higher entropy, higher randomness. And that's what's driving our gases to mix. The formation of a solution is favorable by increasing the entropy. So they actually mix because they are increasing entropy, and that's what the universe wants. The second factor is your intermolecular forces. Your intermolecular forces are forces of attraction that can be between the solute and the solvent. It depends on how strong these intermolecular forces are. So let's talk about some solutions. The intermolecular forces between solute and solute particles must be strong enough to compete with those between the solute particles and those between the solvent particles. So that's like a mouthful. What really is that saying? That saying is that you're dissolving, say, sodium chloride in water. In order for a solution to form, you have to break apart the water molecules from, so you say two molecules, you got to break those two molecules apart so you have space to fit the sodium chloride in. Sodium chloride itself, which is right here, has to separate into the ions, which is what it's doing right here. See, it's separating in the water surrounded. This whole process is called the solution process or salvates. How does a solution form? In an ionic salt, it is soluble in water because of ion-dipole interactions. Where is the ion coming from? The solute, which is ionic. And the dipole is coming from the water. So these partial negative and partial positive charges on the water molecule will actually pull apart the ions from the sodium chloride. They are actually strong enough to overcome your lattice energies. And when that happens, the hydrogen bonds of the water will surround the ions and actually dissolve it. So the attractions involved when forming a solution. Okay, so there are a couple terms that we need to discuss. First, the first interaction is between your solute. So say your solute is sodium chloride. We have to overcome the lattice energy of the sodium ion attracted to the chlorine ion. So you have to overcome and disperse your solute into ions. And in order to overcome that, we have this energy term, which is the enthalpy of your solute, we're going to call it. Now, the second term is your solvent-solvent interactions. Say your solvent is water. Water molecules are hydrogen bonded to each other. You actually have to break those hydrogen bonds to make room for your solute. And the energy term for breaking those hydrogen bonds is delta H solvent. Then you have to have the two come together and mix. That is your solvent-solute interactions. And the enthalpy or energy associated with that, we're going to call our delta H mix, because we're mixing our solute and solvent. So here is a nice graphical illustration of those three enthalpy terms. So simply put, the three processes affect the energy or the energy of the solution process. The first one is separating your solute products. So here you have your solute and you have to separate it. If you are separating it, do you have to put energy in, or is energy going to be released? Well, anytime you're breaking bonds or intermolecular forces, you have to put energy in. So this would be positive or endothermic. The second step is we have to separate our solvent. So in this case, if it's water, we're breaking hydrogen bonding, we're breaking intermolecular forces, and that will also be positive or endothermic. Third step, we're going to take these two and mix them together and have them be attracted to each other and form attractions. When you are forming attractions or forming bonds, you release energy. So this would be negative, and it is exothermic. So let's really describe this in detail. So remember our enthalpy diagrams from a couple chapters ago? Well, this is one of those where the arrows are nice and fat. So remember, we have three processes. The first one is we need to break apart our solute. So you have to put energy in to do that. So energy in, we're going to represent with an up arrow. The second process is you have to break apart your solvent. And that is an up arrow. So these two up arrows will sum and kind of fill this whole gap here. Then your solute and your solvent will mix, joining together. When they join together, they release energy. And in this case, that is the green arrow going down. Now, this example here, the energy that is needed to separate your solute and solvent is exactly equal to the energy that's released when the solution mixes. That's not always the case, okay? But by adding up these arrows, we get what we call our heat of solution. Or you could call it enthalpy of solution. So again, we have our delta H1, which is the separating of our solutes. And that is positive because we need to break them apart. So here's our solute. We need to separate it. We need to put energy in. Positive, endothermic. Second step is, here's our water molecules. We need to separate them, break our hydrogen bonding, so we have spaces in here to fit our solute. So that is also positive or endothermic. The third one is when we mix these two together. They're going to kind of, the orange ones are going to kind of fill in the gaps in the blue one, so on and so forth. That is negative, and that is exothermic, because we are now forming attractions. Intermolecular forces are forming, and we are releasing energy. So what happens when we sum all these up? When we sum all these up, we get our heat of solution. And really, there are three possibilities. This diagram here shows when our heat of solution would be 0. Both of our endo processes, these arrows here, equal the exact amount of energy that is released from our exo. So that would give us a heat of solution of 0. What happens if we add them up and we get an exothermic heat of solution? That means our heat of solution is negative, okay? So let's look at this diagram here. We have our energy to separate our solvent, our energy to separate our solute. When they come together, they release more energy than we needed. Since they are releasing more energy, see this arrow is much longer than these two arrows, this solution is exothermic, and you are releasing heat, okay? If you had this reaction going on in a beaker and you were holding the beaker in your hand, it would feel hot because energy is being released. This process here, exothermic solutions, are spontaneous because your final state, you will end down here at a lower energy. What if you sum them all up and your heated solution is positive? So here again, we have our energy to separate our solvent, our energy to separate our solute. They mix together, and then they release energy. Now we are releasing less energy than we needed to put in to get them to separate. This here would be endothermic. And if you were holding this reaction in a beaker, it would feel cold. Since endothermic solutions end at a higher energy state, how on earth do they proceed? They're not like our spontaneous exothermic solutions. Well, for endothermic reactions to occur, our heat of mixing must be close to the sum of these two. And then there's also the entropy effect. Remember, we talked about entropy a couple slides ago. That is randomness. By having them mix together, we are increasing our entropy, and that helps lower the whole energy state and makes this reaction actually go. So why do endothermic processes occur? Again, we said that they're ending at a higher energy state. Why do they occur? Things do not tend to occur spontaneously without outside intervention. So unless the energy of the system is lower. Okay? Yet we know that if we are mixing ammonium nitrate, that is endothermic, and heat is absorbed and not released. If reactions prefer to end at a lower energy, why would this proceed? What piece is missing? So we talked about it on the previous slide, and the piece that is missing is entropy. Entropy is represented with the letter S. So a lot of times you'll see delta S for a change in entropy. And this is randomness. So enthalpy is only one part of the picture. Enthalpy, remember, is our delta H. Okay, we have to have now our delta S, our entropy. The reason is that increasing the disorder or randomness is known as entropy. And as a system, when you are increasing your entropy, it tends to lower the energy of the whole system. So even though your enthalpy may increase for endothermic reactions, the overall energy of the system will decrease because it's becoming more disordered. So it will occur. Now be careful. Not every aqueous solution when you mix a solid with a liquid is, not every time you mix a solid with a liquid do you form an aqueous solution. Sometimes you're actually forming a chemical reaction. So you have to be careful and really look at what you're doing. So just because the substance disappears when it comes in contact with a solvent doesn't necessarily mean it dissolves. Sometimes it could have reacted. And here's an example. You have nickel plus hydrochloric acid. So here's your nickel metal. You're going to put it in a test tube that has hydrochloric acid. It's going to actually react, and it's going to make hydrochloric acid and hydrogen gas. If you look closely, there's tiny little bubbles here. That's evidence of a chemical reaction. So that should be a clue to you that this is not just a dissolving process. Also, when you let the solvent evaporate, you do not get back shiny nickel. You get this green nickel chloride hydrate that's sitting here. So most of the times when you have a solution, if you let the solvent evaporate, you will end up with your solvent back. Because dissolving is a physical change. So when you reverse it, you should get back what you started with. So when we are making these solutions, we take our solute and we add it to our solvent and we form a solution. Okay? Now, I just said that if we wanted to check and make sure we made a solution, we could let the solvent evaporate. And once the solvent evaporates, we'll be left with a crystal that was our solute. So the opposite of forming a solution, adding your solute plus your solvent, will be to let it crystallize. Go backwards here. Okay? And when we let it crystallize, you're going to separate into your solute, which would be your crystal, and your solvent will evaporate away. So the solution making process and crystallization processes go in reverse order. They're opposing processes. And you might have done crystallization before. Have you ever made rock candy? That is a crystallization process. When the rate of the opposing process is equal, when these rates are equal, okay, adding a solute will not dissolve unless some crystals form. And this is called saturation. So what does saturation mean in normal terms? It means you took some water, you added salt to it, you keep adding salt to it, and then you added some more salt to it and it doesn't dissolve anymore, but instead it sinks to the bottom and you have a precipitate sitting there or a solid sitting there. So when you have a saturated solution, you have added the maximum amount of solute that the solvent can hold. So the solvent holds as much solute as possible. That is what saturation means at that temperature. And it's in dynamic equilibrium with the solute. The solute is in equilibrium with the salt. This process here, the solute that's in liquid is in equilibrium with your solid solute. So it could kind of, this could go into solution only if this comes out of solution. That's what dynamic equilibrium means. If we have not yet reached this point where our solvent is holding the maximum amount that it can, then we say we have an unsaturated solution. So this is holding less than the maximum amount of solute. And you see here, there's a couple solute particles, but it could still hold way more. So this is not saturated. This is unsaturated. The third type is what we call supersaturated. And this is, does not occur as common as your saturated and the unsaturated. In supersaturated solutions, you have tricked your solvent to hold more than it normally should. So normally what you do is you heat a solvent to a high temperature. You dissolve your solute in that high temperature. Normally, most solvents can hold more solute at high temperatures. Then you let it cool slowly, and you get an unstable solution. Here's your unstable solution. As soon as you touch it or drop a seed crystal in it or scratch the beaker, it will immediately, it's very cool if you've ever seen it, start to form crystals, and that's what's happening here. It's immediately crystallizing. It'll crystallize out all of the extra solute that was dissolved, and you will be left with this liquid that's sitting on top is saturated. That is holding the maximum amount. So what affects solubility? Well, first of all, solubility is the maximum amount of solute that a given solvent can hold at a particular temperature. Okay, so what will affect our solubility? How our solute and solvents interact with each other. What forces are there? Are they similar forces? Okay. Pressure will affect solubility only for gases. Only for gases. I can't emphasize that enough. And the third one is temperature. So you have your solute-solvent interactions. And I've said this before, and I'm sure you've heard it before, and it always sounds silly, but like dissolves like. That's a simplified version of what's going on. So what does that mean? That means your polar substances will tend to dissolve other polar substances. And nonpolar substances will tend to dissolve nonpolar substances. But that doesn't really explain everything. That's an oversimplification of it. Okay? What you need to realize is the stronger the solute and solvent interactions, so most of these interactions will be your intermolecular forces. The stronger your intermolecular forces between these two particles, the greater the solubility. Okay? And in this table we have gases, and you notice what's happening with your gases here. Your solubility is increasing as we go down here, increasing. And what else is increasing? Your molar mass is increasing. Okay, so for gases only have dispersion forces as their intermolecular forces. Okay, at least the gases in this table, they're all nonpolar. So the larger the gas, the more soluble it is in the water because the larger your London dispersion forces. Remember when we learned about the larger your molar mass, the more electrons you have, the more polarizable you are, the stronger your London dispersion forces. And that is true here, and that also means that you will be able to dissolve more of this gas in water. What about dissolving other organic molecules in water? So as long as your organic molecule is polar, it will dissolve in water. Much better than a nonpolar organic molecule. Okay? Hydrogen bonding, if your organic molecule has hydrogen bonding in it, it will increase solubility even more. Okay? So here are two examples of organic molecules. Glucose, which has these OHs on it. See these OHs here? That means it's going to hydrogen bond. And you have cyclohexane. There are no OHs here, and there really are no polar groups on here, so this is nonpolar. This here is polar, and it has hydrogen bonding. So glucose will be more soluble or very soluble in water, while cyclohexane, which only has dispersion forces, is not. It will not dissolve. So continuing with our solvent and solute interactions here, the more similar the intermolecular attractions are, the more likely one substance is to dissolve in another one. So if it helps you to remember, like dissolves life, that's where we're going. Okay. So if you look at this table here, all of these have hydrogen bonding. But what do they also have as we're going down? As we're going down, our London dispersion forces are increasing. And they are not only increasing, but they're going to end up dominating over our hydrogen bonding. And what do you notice about your solubility in water? First of all, it's infinite here, so it is very soluble. But as we go down, our solubility is decreasing. So in water, as we go down, as London dispersion forces increase, we become less soluble in water. What about in a nonpolar solvent? What do you notice is happening as we go down? Our solubility is increasing. And why is that? Because what is the only forces that occur in our nonpolar solvent? London dispersion forces. So the more our molecule has similar forces to our solvent, the more it's going to dissolve. So that is why as your London dispersion forces increase, which is the only intermolecular force that occurs in nonpolar substances, the molecule will become more soluble in a nonpolar solvent. And this has some important biological results, okay? So everybody knows what vitamins are. Some vitamins are more important to take than others, where you have to take them even more frequently. So some vitamins, like vitamin A, is a fat-soluble vitamin. Now remember, fats are oils, and they are nonpolar. So if vitamin A is dissolving in a fat, that means it is nonpolar. So they are both nonpolar, okay? So that means that if you take vitamin A, or you eat something with vitamin A in it, it will readily absorb in the fatty tissues in your body, and it will last or stay in your body longer. Because our fatty tissue stays in our body for a much longer time. Other vitamins are water soluble, so they are probably polar. Here is our vitamin C, and look what we have. Look at these tails hanging off. Okay, so it's more polar, so it's going to dissolve in water. Vitamin C is something that you would have to make sure is in your daily diet, because water comes into our system, into our body, and leaves it on a daily basis. So you will not be able to store vitamin C in your body as much as you could store vitamin A. So what about liquid-liquid solubility? Not all liquids will dissolve in each other. So here we have hexane, which is nonpolar. And here we have water, which is polar. So polar that it's hydrogen bonding, right? And you can see a distinct line here where the two do not mix. If they do not mix, that is called immiscible. If they mix and are always soluble in each other, that is called miscible. So this would be like an alcohol in water. So we talked about our intermolecular forces or our solvent-solute interactions, how it affects solubility. And what about pressure? Now remember we said pressure affects only gases. I can't emphasize that enough. So how does it affect gases? The solubility of a solid and liquid are not affected by gases, okay? But gas's solubility is affected by pressure. And what we see here is a carbonated beverage, okay? As soon as you open the cap, you start to see the bubbles. Why is that? When you open the cap, you are actually lowering the pressure, and then the bubbles appear. So think about that for a minute. When you have lower pressure, the gas likes to jump out of the liquid. That means you're decreasing the solubility. So low pressure, less solubility of gas in your liquid solvent. And how are they actually related? Well, there's Henry's law, which explains this. Basically, it says the solubility of the gas is proportional to the partial pressure of the gas above the solution. Look at it. It's very linear. Okay, as your pressure increases, your solubility increases. And here is Henry's law, where Sg is the solubility of the gas. G is for gas. K is a constant, called Henry's law constant. And Pg is the pressure of the gas. As the pressure of the gas increases, so if Pg increases, your solubility will increase. And that's what's showing here. Here's low pressure, and you only really have 3 gas molecules dissolved. You're putting higher pressure, now you have 4. Even higher pressure, now you have 1, 2, 3, 4, 5, 6 are being dissolved. So the higher the pressure, the more gases it will dissolve. The last thing that affects it is temperature. Okay, and let's look at this top graph. Here we have the solubility versus temperature. Most of these substances, what is happening as we raise the temperature? Okay, for most solids, the temperature increases, the solubility increases. However, clearly this is not true. Look at this one here. Here's an exception. In chemistry, you have these exceptions, right? So not all. Notice it says most. Most solids, as temperature increases, solubility increases. But there are some exceptions. And this goes back to our heat of solution. If your heat of solution is positive, or endothermic, then as the temperature increases, solubility increases. If your heat of solution is negative or exothermic, as temperature increases, your solubility will decrease. Let's look at this bottom graph. Look at our solubility to temperature. What is happening? It's decreasing. But what do you notice all of these substances are? Gases. Okay? So for all gases, as the temperature increases, the solubility decreases. If you ever drank warm soda, you feel that tickling on your tongue. That's all of the dissolved carbon dioxide coming out of the soda. Okay? Also, cold bodies of water will have a higher oxygen content than warm bodies of water. And that is the end of overview part 1.